This is Team 52. Our project topic is sepsis prediction by exploiting longitudinal data. Sepsis is one of the leading causes of mortality in hospitalized patients. Traditional scoring system aiming at generating risk scores only take one-time laboratory records into account and does not track the trends of a patient's. Recently, big data-driven approach has been applied to sepsis treatment, and it shows that the approach outperforms existing clinical decision rules. One of the shortcomings of current machine learning algorithms is that it works only on time-invariant data. So our goal in this project is trying to use 12-hour observation to predict if sepsis will occur in the next 6 hours. The innovation in our project is that we will exploit longitudinal data on patients' electronic health records, and we also relabel sepsis with onset time instead of directly using ICD-9 code. Furthermore, we are leveraging the time-dependent nature of sepsis in prediction model. Here is our experimental setup. We will extract the EMR data from Mimic3 clinical dataset and store them in the post-GRE database. And next, we are doing our data preprocess through Apache Spark in Scala and Python pandas. Finally, we'll utilize all the data we gathered to train our model for sepsis prediction. We are implementing our machine learning model and deep learning model through sklearn and PyTorch. The data preprocess procedure is showing here. We are retrieving pivoted vital data and the SOFA scores from the Mimic3 dataset. Here, pivoted means we have data recorded each hour. Then we are calculating the sepsis onset time from SOFA scores. After we get the onset time, we are going to label the vital data with it. For the labeled vital data, we have the statistics of ICU stays with sepsis and without sepsis listed here, and the feature includes 8 vital signs and 2 base variables. In order to cooperate with deep learning techniques, we need to balance the data fed to the model. Because we have a prediction window of 6 hours, so we are only using data which is longer than 6 hours. In that case, we filtered all our records longer than 6 hours and balanced them with the same size of sepsis data and non-sepsis data. Then I'm going to talk about how do we determine the sepsis label. Actually, we observed the SOFA score from 2 days before the suspicious infection time of a patient until 1 day after that infection time. If the score increased more than 2 within the time window, we are considering this patient have a sepsis onset. And also we need to make sure that the window is located within patient stay in ICU, which means the time window should start after the admit time and ends before the out time. In order to determine the observation window and prediction window, we are calculating a distribution of ICU stay hours with each patient, which is shown in these slides. As we can see, most of the ICU stays have 24 hours of data. Since a smaller window size will yield us a better model performance, so we are reducing that time window to 12 hours. As for the prediction window, we found out that many hospitals are applying a 6-hour bundle treatment to sepsis patients. So 6 hours should be a good timestamp for us to see if any changes to a patient with sepsis. Too short prediction window is meaningless because we do not have enough time to change the treatment or apply other methods. The index timestamp shown in the figure is 6 hours before the onset time for a patient with sepsis. For a patient without sepsis, the index timestamp is just the last recorded time. For the machine learning approach, we are splitting the training set and test set as 80% and 20%. We are using a 5-fold cross-validation on our training dataset. First, we are calculating a feature importance, trying to rank different features in order to eliminate unrelated features, which does not affect a lot on our model. Then we are trying different classifiers such as decision tree, random forest, and also with some ensemble method like AdaBoost or MLP. We tune our parameters through grid search and evaluate the performance of our model by ROC-AUC scores. Here in the table shows the parameters we have tested and the best parameters we get after the grid search. For the deep learning approach, we have 70% of the dataset for training, 10% for validation, and 20% for test. Since some of the feature sequence could be less than 12 hours, so we need to pad the sequence. Our LSTM model is composed of a fully connected layer with a hyperbolic tangent activation function, followed by a LSTM layer and a fully connected layer with 2 units. We tried our LSTM model with 5 different combinations of parameters, and we have a comparison of results for 5 models listed in the table on the right side. Finally, we compare all the results from all different models we have tried. The matrix comparison is showing in the table. Among all 4 base classifiers, MLP performs best while decision tree performs worst, but LSTM model surpasses the best score of all 4 base classifiers. LSTM model could get a ROC score as high as 0.92, which means our LSTM model has an excellent capability to predict the sepsis. From all the experiments we have done, we could draw a conclusion that machine learning approach could indeed assist to predict sepsis onset. And ensemble learning is better than the weak classifiers. And our deep learning method using LSTM model considering longitudinal data can lead to significantly higher prediction metrics, which means deep learning method exploiting longitudinal data can perform way better than basic machine learning method. And doctors could benefit a lot from the deep learning method while treating patients with sepsis. There also exists some implementation that we could further improve in the future. Currently, we are using the most recent value to fill the missing entries in our Mimic3 data. Instead of that, we could explore other solutions. And in addition to basic vital informations we get from this Mimic3 dataset, we could consider more features like medicine records, laboratory records, and so on. Last but not least, we could explore different combinations of observation window and prediction window, see if we could further improve the performance of our deep learning model. That's the end of our presentation. Thank you.